The next topic is Bode plot. Bode plot is nothing but it's a systematic way of representing frequency response of a system. How a system behaves with respect to frequency, that's what we're going to see by using Bode plot. To draw a Bode plot, it's a graph basically. We're going to use a semi-log sheet. Semi-log sheet is a graph. Let me see if I can find it right here. So here is a semi-log sheet. What is the difference between a logarithm sheet and semi-log sheet? In semi-log sheet, the x direction, see, the distances are not equal, but when it comes to y direction, the distances are equal. So that's the reason it is called semi-log sheet. Okay, I will go over it one more, again in few minutes. Now, so this Bode plot is based on the logarithms, so it's a good idea to review some basic logarithms. Logarithm of p1 times p2 is nothing but log p1 plus log p2. Logarithm of p1 over p2 equal to log p1 minus log p2. Logarithm of p to the power of n equal to n times log p. Log 1 is nothing but 0. Okay, so these are some basic terminology. And now here is an example. I will go over each point through by solving this example. Here is the given example h of s, which is nothing but a transfer function. H of s equal to 200 over s times 2 plus s 10 plus s. Okay, so it's a third order system. So this system is a third order system, number of poles. So this denominator, transfer function of the denominator, is called characteristic polynomial that represents the poles of the system. So here we have three poles, s equal to 0, s equal to minus 2, s equal to minus 10. So whenever you see s equal to 0, it's exactly on the origin, that's x-axis, y-axis. Okay, and remaining two poles are on the left hand side. So whenever it's at the origin, it's partially stable. Okay, yeah, we're not worried about the stability of the system. We're trying to find what is the behavior of the system with change in frequency. Now, step 1, always keep this as s plus 1. Okay, so remove this 2. Same thing, remove this 10. So what I'm going to do, I'm going to pull those 10 and 2 out. So it's going to be 200 over s times, if I pull out 2, this is going to be s over 2 plus 1. If I pull out 10, that's going to be s over 10 plus 1. Okay, so now this is h of s. Now h of s equal to, if I cancel 20 over 200 over 20, which is 10, I will end up with 10 over s times s over 2 plus 1, s over 10 plus 1. Okay, so this is our given transfer function. Okay, so there are 4 individual terms. We're going to end up having 4 individual lines. I'll talk about it in a minute. Now, when we convert this into decibels, or sorry, in Bode plot, we call that as HDB, where dB is decibels. Okay, so first thing, we need to convert this transfer function into logarithmic function. To convert this logarithmic function, we have to say s equal to j omega. Okay, and units of the gain of, or the units for the unit for the power gain is decibels. That's what this dB represents. D deci, B indicates the bells, decibels. Okay, so first thing we need to do is we need to convert this into logarithm format. So when we convert this logarithm format, make sure that all the numerator terms must be added together and all the denominator terms added together, but we must subtract numerator terms minus denominator terms. So when I write it down in the logarithm format, this must be 20 log So here I don't have any j term, so can I put this as 10 plus j0? So it's nothing but 10 plus j0. Okay, s is nothing but j omega, so that's what I'm going to say. Okay, so this s is nothing but j omega, so minus 20 log, so s is j omega, here real term is 0 plus j omega, okay, minus 20 log j omega over 2 plus 1 minus 20 log j omega over 10 plus 1. Okay, so there are 4 individual terms. Now we're going to draw graphs for each term. Okay, now how to draw the graph? Here is a semi-log sheet. The x-axis represents the j omega or omega, imaginary axis. Basically x-axis represents omega radians per second. So basically the x-axis represents the frequency. I would say it's a frequency. We know that omega is nothing but 2 pi f. Omega is nothing but 2 pi f radians per second. F is nothing but the frequency in hertz. Okay, so x-axis represents the omega. I'm going to take omega in the middle line, the x-axis. Y-axis represents the gain. So the gain is in decibels. So 20 decibels, 40, 60, 80 and 100, and it can have negative gain too. So minus 20, minus 40, minus 60, minus 80. Now you have to have a ruler or scale to draw the lines. I already uploaded this on the blackboard, so you can take a printout if needed. Now when it comes to the x-axis, I will start with this value as 10 to the power of minus 1 radians per second, so which is 0.1, 10 to the power of 0, that is 1, 10 square, sorry, 10 to the power of 1, which is 10, 10 square, 10 cube, 10 to the power of 4, 10 to the power of 5. Okay, this is how we're going to take the x-axis terms. Now here, if you look at here, this is 10, so this is going to be 20, 30, 40, this is going to be 50, 60, 70, 80, 90, 100, that's going to be 100. That's how those the x-axis is divided. Okay, so if you look at here, this is 100. Now this is 200, 300, 400, 500, so this is 500, 600, 700, 800, 900, that's 1000. Okay, so this distance is called decade. Okay, that distance is called decade. Now here we have 4 individual terms. Okay, so here is the first term. We're going to have 4 individual lines. Okay, so the first one is 20 log 10 plus j0. So it is independent of omega. This value is constant. So 20 log 10, which is nothing, log 10 is nothing but log 10 base 10, will end up with 1 times 20, 20. So the magnitude of this is 20 at constant, without any slope. There is no slope. It's a constant magnitude. So take a scale or ruler, okay, and draw a line, straight line at 20 decibels per decade. Okay, I'm going to draw a line. Okay, so this one represents 20 log base, log 10 plus j0. Now the next one is minus 20 log j omega plus 0. If you see plus j 20, then it will go up like this, I mean with a positive slope. If you have negative 20, it goes down with a negative slope. That's all. Okay, now I have minus 20 log j omega plus 0. Okay, here there is no real term, it's only imaginary term. Okay, if you have imaginary term, then there won't be any straight line, it's always a slope, but this line is going to pass through 1. So j omega, I can say j omega over 1. This 1, 1, 2, 10, these three are called corner frequencies. Okay, it's called corner frequency. What is corner frequency? I will tell you at the end one more time. Now, so if you look at the second term, there is no real part is 0. It has only imaginary part. Since it has only imaginary part, the line is going to have a slope of 20 decibels per decade. Okay, so I used a scale or ruler to draw this black line. Okay, so here this represents 20 log j omega plus 0. Okay, so it is passing through the corner frequency 1. So this is called corner frequency. Now minus 20 log j omega over 2 plus 1. Whenever you see the real term plus 1, then it will have a straight line. So remember this blue line doesn't have any imaginary term. Since it doesn't have any imaginary term, it's a straight line. Now this black line doesn't have any real term, so it is always having a slope. It won't be any it won't be a straight line at any point, at anywhere. It's always having a slope. Straight in the sense it won't be parallel with the x-axis. That's what I meant. Now here, if you look at third term, let me use different color. Okay, green. So if you look at this third term, 20 log j omega over 2 plus 1. So whenever you see this plus 1, that indicates that the magnitude is going to be 0 until this corner frequency. So corner frequency is 2. Corner frequency is 2 right there. It's right there too. Okay, let me change the thickness. Okay, so that value is 2. Now this line will have a slope of 10 decibels or 20 decibels per decade. Okay, so this distance is decibel. Sorry, this distance is decade. Okay, decade is nothing but from 2 to 20 is nothing but decade, and 20 decibels is from here to here, that's 20 decibel. So you have 2 points, this point and this point. Use a ruler or scale to draw a straight line. Okay, so here the green line represents 20 log j omega over 2 plus 1. Now we're going to have the third line, the fourth line, last one, sorry, 20 log j omega over 10 plus 1. So until 10, since it has a real term and imaginary term, until 10 the magnitude is going to be 0, and then it will have a negative, since it's a negative number, so it's going to have a negative slope of 20 decibels per decade. So this is 10, 100, so this distance is decade, and decibel, 20 decibels is this height is 20 decibels. So we know that this is 20 dB, so anywhere that height represents the 20 dB. Okay, and this x-axis distance represents decibel. My apology, that's a decade. Okay, that's called a decade. The distance is called decade. Now, so from here to here, you have 2 points. Use your ruler to draw a line. So here is the fourth line, 20 log j omega over 10 plus 1. Now we have all individual lines. To find out the response, we need to add them together. Okay. How do we add them? So if you look at here, initial case, so I have 20 decibels because of the first line. At the same time, because of the constant. At the same time, another 20 because of this 20 log j omega plus 0. So the total magnitude here, because of this line, is 20. Because of this line, that's 20. So the magnitude at that point is 40. I'm adding these two lines basically. Okay. Now, if you look at here, what is the total magnitude? Because of this line 20, this is 0. So magnitude till this point, at this point is 20, the resultant magnitude. Now that line is going to continue until this, until the frequency is 2 radians per second. So take a scale and draw a straight line until you reach 2. Now, why am I drawing until we reach 2? Because that's the corner frequency. So the direction is going to change. Possibility, not every corner frequency, but some corner frequencies, the direction is going to change. So that's the reason we need to have that have the line up to the next corner frequency. Okay. Or another way of saying it is, at this point, what is the magnitude? I have 20 and this is some -8 or something like that. So you will end up with 20 minus 8, so 14. So that's what it is. Okay. Now here, from here up to next corner frequency. Okay. Now this is a constant that is already added in this line. Now slope of this line is 20 decibels per decade. Slope of the second line is 20 decibels per decade. So those two are going down. So the total slope, the resultant slope, is going to be 40 decibels per decade. So what is decade? So from here to here, this is a decade. That green line or black line represents the decade. And 20 decibels or 40 decibels is from here to probably here. That's 20. This distance is 20. That distance is 40. Okay. So that's 40 decibels per decade. So I have one point there. The second point is going to be right there. Now I'm going to use a ruler to draw a line, but at the same time I'm not going to draw it till the end. I'm going to draw it up to the next corner frequency. The next corner frequency is at 10. So I'm going to draw a straight line. Okay, but at the same time I'm going to stop it right there. Because here again I have the third corner frequency, so the direction is going to change again. So here, because of this 20 decibels per decade, because of this another 20. So the total slope is going to be 60 decibels per decade. So 20, 40, 60, and decade is here. So this distance is decade. This is 60 decibels. Okay. So now the final line is going to be, this is our final line. Okay. So the thickest line is the final one. Let me see if I can change this color. Okay, so here it is. This is the final graph. This is only magnitude. Now we have to draw the phase angle one. Now this is the magnitude plot. We're going to draw the phasor plot. Now to draw the phasor plot, I'm going to take theta equal to tan inverse of, okay, real over imaginary. I have imaginary over real term. So we have h of s equal to 10 over j omega square. S is nothing but j omega basically. So j omega square plus 1 plus j omega over 2, 1 plus j omega over 10. So theta, the phase angle, theta equal tan inverse of, I don't have any imaginary, so tan inverse of j0 over 10. So this represents this part minus tan inverse of j omega over, here I don't have any real part, so j omega over 0. So I have square here, so minus tan inverse of j omega over 0 minus tan inverse of j omega over 2 over 1 minus tan inverse of j omega over 10 over 1. Okay, so now you can take omega equal to substitute omega value and make sure you substitute every corner frequency. So omega and theta. So I want initial one, so initial one is 10 to the power of minus 1. Okay, and then I'm going to take 10 to the power of 0. And I have 2 as a corner frequency and 10 as another corner frequency. Once we're done with all the corner frequencies, go with 100, 1000, something like this. So find all the theta values for this. So I already found the values, I'm going to copy them. So here theta equal to, before copying them, tan inverse of 0 over something is 0, tan inverse of 0 is 0. Tan inverse of imaginary over 0, so which is infinite, which is 90 degrees. So minus 90 minus 90, so this is basically 180 degrees minus tan inverse of j omega over 2 minus tan inverse of j omega over 10. Okay, now substitute these omega values. I end up with, this is minus 183.43 minus 212 minus 236. My apology guys, I don't think we have j omega square, we have only j omega, so it has only one term. I don't have that second term, my apology. So it's not minus 180, it's minus 90. Okay, so with this I have the omega values at 10 to the power of minus 1. I'm going to draw approximate, 10 to the power of minus 1, which is 0.1 approximate values here. So minus 90, this is 0.1 over 2, very small number, 0.1 over 10, another very small number. Approximately this is going to be minus 90. Or else I actually have the actual value, which is minus 93.43 degrees. At 10 to the power of 0, minus 122.3 degrees. At 2, minus 146.31. At 10, minus 213.7. At 100, minus 263.14. At 1000, I'm sure this is going to be approximately minus 270. Okay, even at 10,000 it's going to be minus 270 because that's very large number. So tan inverse of very large number approximately equal to 90 degrees. Now we're going to draw the graph here in the graph sheet. So the x-axis, make sure we're going to take the same values as omega, which is 10 to the power of 0, 10 to the power of this is 10 to the power of minus 1. So make sure you follow the same as above. So 10 to the power of minus 1, 10 to the power of minus 1, 10 to the power of 0, this is 10 to the power of 1, 10 square, 10 cube, 10 to the power of 4, 10 to the power of 5. Now the y-axis here, I'm going to take this as minus 180. Okay, when you go up, usually I'll go with 45 degrees, so 135 minus 90, okay, minus 225 minus 270. Okay, now if you look at the omega values at 10 to the power of minus 1, that value is 93. So that's minus 90, so minus 94 is somewhere there. Okay, at 10 to the power of 0, which is minus 122, so minus 122 is going to be somewhere there. Minus 146 at 2, so 35, 146. Those are all approximate numbers. Okay, at 10 to the power of 10, sorry, at 10 to the power of 1, minus 213. So at 10 to the power of 1, 225, so probably 213 is going to be somewhere there. And at 100, minus 263, and at 1000 it's going to be 270. At 10,000, 270. At 10 to the power of 5, 270. So this line is going to be something like this. Okay, I'm drawing it freehand, so it's not touching this point here. Now this is the phasor plot. Now what are we going to do? We're going to do a gain crossover frequency and phase crossover frequencies. So the gain crossover frequency is nothing but at what point the gain is crossing the zero magnitude. So at what point, so the gain is crossing the zero magnitude at that point. What is the frequency at that point? The frequency at that point is 2, 3, 4, maybe 5. Okay, so I would say gain crossover frequency is 5 radians per second or 4 radians per second. So at this point, that's 1, 2, 3, 4, I would say 4 gain crossover frequency equal to 4 radians per second. What is the gain crossover frequency? Why do we need it? Where the gain is crossing 0. That's what gain crossover frequency. Phase crossover frequency is same, where the phase is crossing minus 180 degrees. So it's right there. That value is 1, 2, 3, 4, probably 4.5 or 5, doesn't matter. I'm going to say that that's a phase crossover frequency over frequency, that is 5 radians per second. I'm taking that as 5 radians per second. Now I have gain crossover frequency and phase crossover frequency. Now I'm going to define another term called gain margin and phase margin. So the gain margin here is nothing but the amount of gain which can be increased or decreased without making a system unstable. So I mean, from this, as mentioned, we can tell the behavior of the system. At the same time, we can tell the stability of the system too. So the gain margin is nothing but, say, for example, you're walking on a street. Okay, say the street is very wide. Okay, and you're walking in the middle. So you can go either direction, this much length, without falling out of that street, assuming that street is elevated a little bit. Okay, so here you have very good gain margin. What if you're walking on a straight line? So here, I mean, gain margin is 0. If you if you put your feet, I mean, one wrong step will take you out of the street. Okay, so here gain margin is 0, but here you have very good margin. Okay, so that's what the gain margin indicates, how far or the amount of the gain which can increase or decrease. Now, how do you find the gain margin and phase margin here? So look at phase crossover frequency. So here is the phase crossover frequency. I'm going to draw a straight line. Okay, now here find out what is the magnitude of the Bode plot here. So we need to look this. That will give you gain margin, I believe, which is 8 decibels, because if this is 0, that's 4, 8, 12, 16, 20. So it's look like it is meeting there. Okay, so probably 8 decibels. So here the gain margin is 8 decibels. So you have 8 decibels, you can change up to 8 decibels without making the system is unstable. So the gain crossover frequency is here 8 decibels. Okay, now phase crossover frequency is, we'll find it where the gain becomes 0. So it's right there. Let me draw this line. Approximately it is also same, but it's somewhere there, right? So this is what the phase that's the phase margin. So here phase margin is right there, whatever that number is. I'm guessing probably this is minus 180. Looks like 8 degrees approximately. Okay, that distance is nothing but 8 degrees. Thank you. It's a very long video. I'll stop it here. If possible, I'll go over this example in the class. Thank you.